Hi everyone, so today we're going to start Unit 2. So this is the stuff that goes towards our second test that we will have. And so we're going to start out in Chapter 5 with 5.1, which looks at scatter plots and correlations. So what we're looking at here is when we have two sets of data and we want to find the relationship between them. So two different variables, they can be about anything that we want, and we want to see if there is a correlation between them. We want to see if there is that relationship. This is called bivariate data, okay? Bivariate meaning that there are two variables, okay? And we are looking at their relationship. So bivariate data, looking at two variables and their relationship. When we look at a relationship between two variables, the first thing that you should think of is a graph, okay? And the graph that we tend to use is a scatter plot. So a scatter plot is a useful graph to use when looking at the relationship between two variables. Okay. We tend to label these variables x and y, okay? The x variable is the explanatory variable. We've talked about this before. The x variable is the explanatory variable. And the y variable we call the response variable. Why is that? Well, the x variable should explain a response in the y variable, okay? The x variable normally affects the y variable. So we can say, okay, x explains a reason for the response in the y variable. So x is the explanatory variable and y is the response variable, okay? You could look at, for example, the number of hours that someone studied compared to how well they did on a test, okay? The more hours you study, you would assume that the person did better on the test. So the number of study hours explains the response of how well someone did on a test, okay? There are different types of relationships that you can have between these two variables, okay, when you plot them out on a scatter plot, okay? You can have either a positive relationship, you can have what we call either a negative relationship or an inverse relationship, and then you can just have no relationship at all, okay? When you look at a scatter plot, all we tend to do, and excuse my terrible drawing when I do this, okay, I'll have my x variable on the x-axis, y variable on the y-axis, and then I can plot this out. If you've got a positive relationship, tends to look something maybe like this, okay? It tends to go in the general positive direction. So as one variable increases, the other variable increases, okay? We have a positive relationship. You can also have what they call either a negative relationship or an inverse relationship, in which you can kind of see as x increases, y is decreasing, okay? So this would give us a negative or an inverse relationship. So as one variable increases, the other decreases, okay? And then finally, you can have absolutely no relationship whatsoever between the two variables. So one does not cause the other when we look at this graph. And you'll see when we plot those x, y coordinates, they are just all over the place. Okay, so when you plot these scatter plots, okay, you'll look at, let's say we're looking at the x variable is the number of hours that someone studied for a test, and the y variable is how well they did on the test. It's their score on the test, okay? For a particular person, that would represent one particular dot on our scatter plot, okay? So the X variable, okay, the X value that you would plot is the number of hours that a particular person studied, and then the Y variable would tell you how well they did on that test. So each one of these dots is going to give us one person, okay? It tells you the X value is how many hours they studied, the Y value is their score on the test, okay? So you just plot these X, Y coordinates, okay, to give you these dots on the scatter plot. We also have to look at how strong the relationship would be, okay? None of these are totally linear, okay? You don't have all of your dots in one straight line, okay, in one diagonal line. So if you get something, for example, that looks like this, where all of the dots are in a perfectly straight line, okay, that would be a perfect relationship, okay? You've got a perfect positive relationship here. It's a linear relationship. Okay? They have this perfect linear relationship. This normally doesn't happen, okay? Normally when you look at these graphs, you're going to get something like one of these, where you can see a general direction that the points go in. So overall, they're mostly going in a positive direction, or they've got an inverse relationship, or they've just got no correlation whatsoever. But you very, very rarely see it, but it does happen, where these points have a completely linear relationship. So X and Y have this linear relationship. They've got what we call perfect correlation. So, of course, the stronger the relationship between these X and Y variables, the more linear it is going to look. Okay, so you may find for a particular class, again, this won't happen because of other variables thrown in, but you may find that you could get a completely linear relationship, as the more hours that someone studied, the better that they did on the test. Obviously, that's not going to happen, as we'll see now, okay? So, let's look at this particular example. We are looking at here the pupil-teacher ratio for particular schools versus the high school completion rate. So for these particular high schools, we are looking at the ratio of pupils to teachers, so how many pupils there are per teacher, and we're looking at the completion rates for those schools, so how many people actually graduate. Now, we would assume that the lower this ratio was, okay, so the less pupils you had per teacher, the higher the completion rate would be. But you would expect this relationship to occur, okay? So the less pupils you had to a teacher, the more likely you would say that that school would have a higher graduation rate, okay? You would say that more students would complete because those students could get more attention. We can see here, there's basically no relationship between these two things, okay? You do have some schools where they have a very low pupil to teacher ratio, but they also have a very low completion rate. They've got a low graduation rate. Whereas you've got some other schools where they've got a much higher pupil to teacher ratio, so there's way more students per teacher, okay, which means that they don't get as much attention, but their graduation rates are much higher. So we have this kind of weird situation where we expect there to be this correlation and there is not, okay? Why is that? It's because of a confounding variable at play. Okay. So again, you would expect the smaller the class size, the better that people would do. But you see here, that's not the case. Why is that? Well, you've got many confounding variables at play, okay? You are looking at socioeconomic factors, okay? Particularly in more rural areas, yes, you may have less pupils per teacher, but you also may have less resources, okay? The school may not have as much money to actually put towards the students to give them a good education. So you may not get as high a graduation rate, okay? But then you may have some city schools where yes, they've got much bigger classes, but they have way more resources in order to help these kids get through high school and to graduate. So there's all these confounding variables at play with socioeconomic factors and location and everything like this that actually affect what is going on here. There's those confounding variables that are affecting our relationship between those X and Y variables. Okay. There is another type of thing that you can come across, and that's something called a common response. This is actually the opposite of what we just looked at. Okay. Common response is when you don't expect there to be a relationship between two variables, but it turns out that there is this relationship. Okay. So an example of a common response would be the relationship between ice cream sales and this is really random, and snake bites. Okay. We would not expect there to be a relationship between how many ice creams were sold in a week and how many people got bitten by a snake in a week. Okay. They're two very different variables that we would not expect one to affect the other. Okay. But if you actually go in and look at the data, you actually see that the more ice creams that there are sold in a particular week, the more people are bitten by snakes in that particular week. Why is that? Because of one simple thing called the weather, okay? If it's warmer outside and the hotter the climate you live in, okay, the more ice cream is probably sold because people are really warm, okay? And also the more snake bites there probably are because snakes are more likely to be out in tropical warm weather, okay? So these are two things that are very different from one another where we don't expect there to be a relationship, but there is one because of an underlying variable that we haven't yet considered. But this time it actually causes a relationship between the two, and it doesn't say that there is no relationship between the two. So if we came back to here, okay, our confounding variable meant that there was actually no relationship between these two variables, pupil-teacher ratio and completion rate. But in the common response case, there are two things that we did not expect to have a relationship, but because of an underlying variable, we found that there was a relationship between the two. That is called a common response. Okay. So when we talk about relationships between two variables, there is actually a different word that we tend to use, and you've heard me use it a couple of times in this video, and that is correlation. Okay. Whenever we look at the relationship between the X variable and the Y variable, whatever those might be, we actually say that we are looking at the correlation in the data. Is there a correlation to it? Is there a relationship between those two variables? The thing that we actually use is something called a correlation coefficient. And what this does is it looks at the strength of the relationship between X and Y. Okay. By strength, I mean how linear it is. Okay. The stronger the relationship between X and Y, the more linear it is going to look and less scattered that it's going to look. Okay. So if you have a very strong relationship, it's going to look very linear. Okay. Whether that be a positive relationship or an inverse relationship, that negative relationship, it will still be linear. So you can have a linear relationship and a very strong relationship. It just may be an inverse relationship, in which case it would go like this. So this is a linear inverse relationship. Okay, again, the relationship, that correlation is very strong. You've got a strong correlation here. It's just an inverse correlation because as one increases, the other decreases. So we want to look at the strength of this relationship between X and Y, how linear it is. okay? To find this correlation coefficient, okay, you're going to use this particular formula, okay? I say you're going to use it, the calculator's going to use it, and you're going to plug some stuff in and it's going to do it for you, because you can see from this formula here, it's horrible, okay? You're not going to want to calculate this for a whole data set, okay? You would have to do this for every single data point, X, Y, and then you're going to have to sum all of this stuff together, and it's just a big hot mess, okay? So you don't want to deal with it. Your calculator will do all of this for you. You just need to know exactly what you are calculating, okay? So as I said, it looks at the strength of the relationship. So what we are looking at is how correlated this is. So it will tell us how strong the correlation is. Whether positive or negative or inverse, if you want to call negative the inverse instead. Okay. Now, when you calculate this for a particular data set, okay, you're going to have your list of X values and the list of corresponding Y values. Make sure that the X, Y coordinates match up. So don't make your X or Y data list into some like weird order, okay? Make sure that you put them in the order that they come in, because they match up as X, Y coordinates for one particular thing. So for example, when I said to you, you could have the number of hours that people studied for a test and the scores on the particular test. Or make sure that the X, Y coordinates match up so that the number of hours someone studied and their test score corresponds to one particular person. So don't mix them up in the lists, okay? When you do that, you're going to put those lists into your calculator and you're going to run this thing, as I'll show you in a minute. And it's going to give you a particular value for R, okay, this correlation coefficient. R is always between -1 and 1, including -1 and 1. It can equal one of those values, okay? So let's say that you get a value of R is equal to 1, okay? If R equals 1, that means you have a perfect positive correlation. That means that you have this perfectly linear relationship between X and Y in the positive direction. So you end up with your relationship between X and Y going in a straight line, and it is in a complete straight line. There's nothing that deviates off of that line. There's no data points off of it. They all go in a direct straight line in the positive direction when R is 1. On the flip side of that, when R is equal to -1, you have a perfect negative correlation. So when you would draw it out for your X and Y coordinates, it would look something like this, okay? Again, they all lie in a direct straight line, but this time they go in a negative direction, okay? But you still get this linear relationship between X and Y, it's just negative, okay? If R is equal to 0, so we've gone from R is 1 to R is -1, okay? And R is always between those two values somewhere on the number line, okay? 0, which is directly in the middle of these two, okay, would mean that if R is 0, there is no correlation between the two. There is no relationship between X and Y. So if R is equal to 0, it means that you are looking at a scatter plot of X and Y that is just all over the place. Okay, would look something like that. There's no relationship. And you actually have no correlation. Okay, it's not linear, there is no relationship. Okay, now, if R is equal to 0 means you have no relationship, And R is equal to 1 means you have a perfectly positive correlation. So you've got this perfectly linear relationship between X and Y. What happens if you fall somewhere between 0 and 1? It means that your points are somewhat scattered, but overall they still go in that positive direction. And the closer that you get to R is equal to 1, the more linear that relationship is going to look. Okay? So I can start out with something that would look like, I don't know, let's start with R is equal to 0.3. Okay? It's a positive value, which means that overall our correlation and our relationship between X and Y is mostly positive, but it's still closer to 0 than it is to 1, meaning that our points are still kind of scattered all over the place. So you would probably find if you had R is equal to 0.3, your values, they would still go somewhat in a positive direction, but they are still kind of spread out, okay? You've got more spread to the data than you really want. But the closer you get to 1, the closer these points are going to get to that linear relationship, the closer they're going to get to a straight line. So if I had, let's say, a correlation coefficient value of 0.8, then you may see that these values actually fall more into a line. So you would get maybe something like this, okay? They don't lie on a direct straight line by any means, but they are getting closer and closer and closer to actually falling on one direct line as though R were equal to 1. So the closer R is to 0, the more of a scattered relationship that you will get. But again, if it's positive, you would still end up with the data points going in more of a positive direction. And the closer and closer R gets to 1, the more it's going to form a straight line. Okay, the closer it's going to get to having a linear relationship. On the flip side of that, let's look at some negative values. Okay, again, when R is equal to 0, we have no correlation, we have no relationship between X and Y. But when R is equal to -1, it will form a perfect straight line, but in the negative direction. Okay, it will have a negative slope. So what happens if we had this time R is equal to -0.3? Okay, well again, we're closer to 0 than we are to -1, which means that this stuff is going to be more scattered. Our data points are more scattered than we really want, okay? But they still have a general negative direction, a negative correlation to them. So when I look at my data points, again, they're still really scattered, but in general, they go in that more negative direction, okay? The closer we get to -1, so let's go with -0.8. Again, when we draw this out, because we are closer to -1 this time, the closer these points are going to fall to being on a direct straight line, okay? But again, in the negative direction. So, moral of the story, the closer you are to 0, the less of a relationship there is between X and Y, okay? If you get a positive R, there is an overall positive correlation. If you get a negative R, there is a negative correlation. The closer you get to +1, the more of a positive correlation there is. The closer you get to -1, the more of a negative correlation there is. The more linear it's going to get in either the positive or negative direction, respectively. Okay. There is actually a great video that looks at these graphs and looking at this correlation coefficient, this R value. It's one of the Against All Odds videos on correlation. I'm going to link it in the Against All Odds videos tab in Blackboard, so you can go ahead and watch that. It isn't very long, but it is a very good video that looks at this R value and looks at these changing graphs if you would like some extra information. So I highly recommend you go ahead and look at that on the Blackboard page on the Against All Odds videos. I'm going to show you how to do this using a calculator, because you do not need to, if we look back at our correlation coefficient, you do not need to calculate this thing by hand, okay? It's a horrible formula and I would never ask you to do it by hand. but our calculator will do it for us. And our calculators will actually also calculate the line of best fit that goes through our data points, which we're going to look at later on. And you can actually also plot your scatter plot, okay? So there's many different things that you can use the calculator for. I'm going to show you a couple of them just so that you can see how it works for your homeworks, and also show you where you're going to find your line of best fit formula that's going to come up in a couple of sections time, because that actually comes up in the same menu. So we can go ahead and do all of that on our calculator. I'm going to use this example for the calculator problem, okay? It's the amount of drug that someone takes and the reaction time, how long it takes them to react to the drug given the amount that they have taken, okay? So for example, if someone took 4 milligrams of this drug, it took them 0.7 seconds to react to it, okay? So we're going to go ahead and put this in our calculators in two lists, and we're going to see if we can find the correlation coefficient and find the line of best fit, which again will come up in a couple of sections time, so don't worry too much about that right now. But we're going to find that correlation coefficient, and we're also going to plot a scatter plot on our calculators. So make sure you can go ahead and put these as two lists in your calculator now, and then we'll use this data on our calculators. Okay, so what I've gone ahead and done, if we look in Stat and Edit, in list 1, I've put that list of the milligrams of drugs. So 1 through 10 was the milligrams of the drugs. And list 2, I've made the reaction times. So you can see for each one of the milligram measurements, I have the reaction time it took for the person to react to that particular dose of the drug. Okay, so you'll see, for example, for 6 milligrams, it took the person 0.8 seconds to react. Okay, so we have our XY coordinates put in. Your X coordinates are in list 1, your Y coordinates are in list 2. What I want to do is to find both the scatter plot, and then I'm going to go ahead and find that correlation coefficient, and I'll actually find my line of best fit. Okay, to do this, I'm going to quit out of this for now. And the first thing that you need to do whenever you deal with scatter plots and you deal with that correlation coefficient and lines of best fit, you must make sure that something called diagnostics on your calculator is turned on. If not, this will not work. So to do that, what you're going to do is you're going to go to second and catalog, which is on the 0 button. So second and 0. Okay, this is going to basically give you a catalogue of everything in your calculator. You need to scroll down to diagnostics on. Okay, you can actually go to the green button here and then click D, which is on my matrix button here. So do that, and it will go down to D for you. It saves you scrolling all the way through, but you can if you want. And then go down to where it says diagnostic on. Okay, make sure you go with on and not off. Once the arrow's on that, click enter and enter. Okay, once it says diagnostic on and done, you are good to go. So I'm going to clear that screen. Now, first thing I'm going to do is to actually plot the scatter plot. So we've got our list of X values in list 1 and our list of Y values in list 2. So the way that you do this is we're going to use that stat plot function again. So I'm going to go to second stat plot. Okay. Now make sure that all your other plots are turned off. I just want plot 1 turned on, because we are only plotting one graph here. I'm not plotting multiple graphs on top of one another. Okay, so make sure plot 1 is turned on, but if you come over to plot 2, it should be turned off, which it is, and then plot 3 should also be turned off. Okay, I just don't want anything plotting over the top of this. So plot 1 is the only one turned on. Then when you go to the type of graph you want, it's actually the first one, okay, where we see all the dots. Okay, that is a scatter plot. So the type of graph we want is the scatter plot. Then whichever list you have put your X variable in, put that in there. So mine is in list 1, it already says list 1, but I would just do second and 1 to give me list 1. And then I've got my Y list, my Y variable is in list 2, so that's all good, okay? And you can pick how you want it to plot, whether you want a cross, a dot, etc. It doesn't matter. Okay. Now, once you've done that, exactly the same as we did with the box plots. Okay. Once you're on the screen, just go to zoom here and go down to number 9 and it will plot. So you just do zoom and 9 and then it plots it. Okay. Let's look at what we actually have from this scatter plot and what this tells us about the data. Okay. You can see we have an overall positive relationship. Okay. It generally goes in that direction. It's just that they are kind of slightly scattered. They're not too scattered. They're not too all over the place, but they do have this general positive direction. So what would we consider our R value to be, our correlation coefficient? Well, I would say from here, okay, it's going to be pretty close to 1, but it's not going to be quite there, okay, because we've still got some of these scatter points. So I would say it was closer to 1 than 0 because we can see this overall general direction is pretty obvious, okay, as the X variable increases, the Y variable increases, but we do still have some variation in here. It is not on a direct straight line. So I would say that my R value was probably going to end up being closer to 1 than 0, okay? How do we find this, okay? How do we find that correlation coefficient? Okay, I'm going to quit out of this for now. And then what I'm going to do, I'm going to go back to stat here. Okay, this is the menu that we've come into before. So I'm going to stat, I'm going to go across to calc. Now everything we've done before has been in one variable stats. Okay, I'm actually going to come down to option 4. You can go to option 8 if you want. It will make no difference for what we are doing today. When we come down to our line of best fit, you can use either 4 or 8, but it's just going to be that your coefficients of X are going to be the other way around, but we'll talk about that later on. But for right now, you can use either number 4 or number 8. You will get the same result for what we want today. So let's go down to number 4. Okay. Whichever list your X variable is in, goes in there. My Y variable is list 2. I'm going to keep both of these blank right now. We will actually use store reg EQ later on. But right now I'm going to keep both of those clear. And then I'm going to go down to calculate. Okay. And it's going to bring up this whole menu of stuff. Now, A and B are going to help us with our line of best fit later on. Okay, Y is equal to AX plus B. That is our line of best fit that we're going to talk about in a couple of sections' time. But right now, I just want to look at my R value. Okay, it's this bottom value here. R squared, which is literally just this value squared. We're going to deal with that later on as well. But we only need our bottom value right now, that R value. And it comes out to about 0.75. That is what we expected, okay? We expected from looking at that graph that it was going to be positive, okay? And we said it was going to be closer to 1 than 0 because we had this overall general positive direction, but there was still some variation to it, so it wasn't quite 1. So 0.75 sounds about right, okay? So this calculator will do all of that calculation for you. All you have to do is to put the lists in the calculator, go to stat, calc, number 4, put your X variable in there, your Y variable list in there, and then you just go ahead and calculate and it will run all of that for you. So it's super simple, okay? Just be aware that kind of like from what we were talking about before, when we looked at means and medians and we looked at outliers, this R value is significantly impacted by an outlier, which makes sense. Okay, let's come back to our plot here. Okay, our scatter plot. Okay, if I had some random outlier that was all the way up here, okay, that means I have more variation in my data, okay? That means that my points are more spread out because I have another point that is way off of the others. So that means that when I look at my R value, it's going to say that my points are more spread out, which means that my R value is going to be closer to 0 than we initially expected because we have this outlier that is making our data look more spread out. So your R value is drastically affected by these outliers. So bear that in mind whenever you do get a question about whether outliers affect this correlation coefficient. They do because it makes the data more spread out. Therefore, the R value is going to be closer to 0 than you initially expected. Okay. There's actually another reason why we like the R value, this correlation coefficient in statistics, and that is that it has no units, okay? All it does is tells us the strength of this relationship, the strength of the correlation between X and Y. It does not actually matter what the units of the X variable and the Y variable are. It has no units. R has no units. It just tells us the strength of the relationship between those two variables. So that's why it's very useful in stats, because it's a unitless value that just looks at the strength. Okay. That is everything from 5.1. If you have any questions whatsoever, please let me know and I will see you in the next video.